In this lesson we're going to look at the arrhenius definition for a base. In the last lesson we looked at the definition for an acid, and what we'll say here is that bases are substances that produce hydroxide ions when dissolved in solution. Now you might find that a bit surprising because you'll probably remember in the penultimate lesson we looked at a very clear-cut definition of a base and an alkali, and we stated in that definition that bases are substances which neutralize an acid to produce a salt but are insoluble in water. So bases are insoluble in water. So strictly speaking, what we're referring to here are alkalis, because bases aren't soluble in water and therefore don't produce hydroxide ions. However, the terms base and alkali seems to be so interchangeable in most curriculums, in most textbooks, that what we call an alkali is a base and what we call a base is an alkali. And so although we're using the word base in this definition, strictly speaking we're referring to alkalis. Okay, so we're going to continue using the word base rather than alkali in this lesson. So as with acids, we need to ask ourselves, what do we mean by a strong base? What do we mean by a weak base? So first of all, a strong base. So a strong base is a substance which will virtually 100% ionize in solution. And an example of that is sodium hydroxide. So what we mean by that, if we get some crystalline sodium hydroxide and we dissolve it in water, then it will 100% ionize. Let's say 100% of the hydroxide ions in the crystal will go into aqueous solution. So you get 100% ionization. And that means that if we start with 1 mole of sodium hydroxide, we add it to water, then we will get 1 mole of hydroxide ions produced. So, the common strong bases are the group 1 bases, for example, potassium hydroxide, lithium hydroxide, and calcium hydroxide, also known as lime water. Now, what do we mean by a weak base? Well, a weak base is a base that doesn't fully ionize in solution, or a weak alkali is an alkali that doesn't fully ionize in solution. So for example, the case of ammonia, which is a gas dissolving in water, well, that will produce aqueous ammonium ions and aqueous hydroxide ions. However, 99% of the ammonia will remain unionized. It will remain in its covalent state as the gas dissolved in water, and only about 1% of the ammonia will ionize into the ammonium and the hydroxide ion. Okay, so we can say 99% remains in solution as a dissolved gas. Only about 1% is converted into the hydroxide ion. So this is classified as a weak base. Other examples of bases which are not strong bases would be, for example, sodium carbonate, which dissolves in water to produce aqueous sodium ions and aqueous carbonate ions in solution. And then what happens then is that these carbonate ions will then attract the hydrogen ion from the water to produce the bicarbonate ion plus a hydroxide ion. So sodium carbonate indirectly results in the production of hydroxide ions, but this is not a complete ionization process. Alright, so for example, 1 mole of sodium carbonate dissolved in solution will not result in 1 mole of the hydroxide ion, for example. So this is classified not exactly as a weak base, but for example as a medium base. Now, a weaker base than sodium carbonate is sodium bicarbonate. You'll notice that we've got a single arrow here which indicates that the sodium carbonate is fully soluble. I should put this when dissolved in water. That's to say, it completely ionizes into the sodium ion and the carbonate ion, whereas the bicarbonate ion not so. So for example, go to your kitchen cupboard, get a jar of baking powder, get a teaspoon of baking powder, put it into water and stir it around. You'll notice that it doesn't completely dissolve, whereas soda suds or sodium carbonate will. So for that reason I've got this reversible reaction sign here, so it's not fully soluble. And so that ionizes into the sodium ion, aqueous sodium ions, and aqueous bicarbonate ion. Now the bicarbonate ion will then go on to form carbon dioxide gas and hydroxide ions. So going back to our little experiment with the baking powder, what you will notice first of all is that baking powder doesn't completely dissolve, right? That's justifying this back forward arrow here. And then you'll also notice then that if you look very carefully, you're going to see very tiny little bubbles being released in the solution. These are tiny little bubbles of carbon dioxide. So this process here going on in this second phase, it's not a strong decomposition, so there's only a small amount of carbon dioxide being released, and likewise there's only a small amount of hydroxide ions being formed. But you will notice that these are present, because if you put your hand in the solution, you will feel immediately that you've got that recognizable soapy touch associated with the hydroxide ion, the production of the hydroxide ion. Likewise with the sodium carbonate, these are known as soap suds. Okay, so you get that with the sodium bicarbonate too, but there won't be as many of these produced as there are in the case of the sodium carbonate. Okay, that kind of makes sense, because if you look at this equation here, well, we've got our hydroxide ion here in this step, but then this one, again, following what we've just written here, this will then decompose into more hydroxide ions. So you're going to get a stronger concentration of hydroxide ions with the sodium carbonate than you do with the sodium bicarbonate. For that reason, this has got a higher pH. This pH is round about 11, and the pH of the bicarbonate is round about 8, 9. Anyway, we'll talk about pHs in a later lesson.